For joining a webinar this morning. The topic of performing arc flash risk assessment with focus on wind farms and solar farms. We have presenter John Kolak here this morning with us, and both on LinkedIn, YouTube, and also Facebook channels. As you're going through the presentation, please feel free to type in your questions, and John will answer those questions at the end as time permits. So without any delay, I will turn it over to John.
Thanks, Banu. Good morning, everyone. What I wanted to do before we get in too deep into the presentation is sort of set the table for where I'm coming from with the presentation, and then we'll run through the slides. And again, as Banu mentioned, definitely type in your questions, and I'll answer those in real time if I can. And if I don't know the answer, I'll get the answer for you, and we will send that out to you via email later on. My company, Praxis Corporation, has done probably about 75 or so arc flash studies on everything ranging from transmission systems to large industrial facilities to solar farms and wind farms, of course. And so I wanted to sort of explain that a lot of what I'm presenting to you today is lessons learned from either things we've done and worked out kinks in the process, so to speak, or things that I've seen other engineers do that I thought were clever or helpful. But I don't want to suggest that I'm the gold standard in telling you how to do an arc flash study on a wind farm or a solar farm. But I would rather approach this sort of as co-practitioners with you, those of you that do wind arc flash studies, and give you sort of tips that I thought were helpful, and hopefully, as I said, to be able to answer any questions that you may have. So with that, let's move to the next slide. And the next slide is not moving. There we go. So sorry about that. So I said this presentation isn't only for engineers, is the suggestion here, although I will say that it's primarily aimed at electrical engineers who do these kinds of studies. However, if you have responsibilities for seeing that arc flash studies are done, hopefully I'll give you information that will be useful for you as well. But it is generally centered on electrical engineering who do these kinds of studies. But as I said, we'll try and make it practical for those that don't have that level of technical experience or responsibility. I'm going to cover a few important arc flash risk assessment concepts that I think are important to understand. These are helpful to set yourself up for doing the studies properly and getting the best and the most information you can from the arc flash studies. In addition, I'm going to talk a little bit about general safety when it's appropriate, because again, we're not only talking about the arc flash concepts in the sense, but we're also talking about things that can cause injuries to people from shock or other hazards that are ancillary to the kind of systems we're going to be talking about. So we won't limit ourselves only to arc flash risk assessment, especially when it makes sense for example, from a safety training perspective. Of course, we're going to talk about the unique hazards that exist on wind and solar farms. They're configured in very unique ways, and so because of that, they present unique hazards, and modeling them requires some pretty thoughtful approaches on that. And as I said, I'll share with you things that we've done, but I'll also steal shamelessly from other engineers who've done clever things that I thought would be helpful to you. So we'll give you our best thinking on the matter, answer your questions, and hopefully this will be useful for you. As far as modeling the solar and wind farms, I'll actually give you a couple of examples of that I've seen. And we'll talk sort of about the benefits and takeaways from those kinds of approaches, and give you some general guidance as to how you can handle modeling these two types of systems, and they're quite complex. We'll also avoid some arc flash risk assessment traps, and when I say that, kinds of things that we do as engineers in the process of doing the studies, and we perhaps take our focus off the things that have the greatest hazard. So when we talk about a risk assessment, we're going to be talking about, as I said, identifying those kinds of things where we hyper-focus on something at the expense of something else that may be helpful to you. And then we'll talk about some next steps, and hopefully the sum of all that, as I said, will be helpful for you. So some basic concepts. One thing that I strongly recommend, and this is also related to available. So rather than doing calculated values, for example, for the short circuit current that can be outputted by a generator or whatever, always get the information from the manufacturer if you're able, and use that information. OSHA always defers to the manufacturers when they have multiple options, and that would be a good suggestion for us as well. It would also be, we'll talk later about using SCADA, supervisory control and data acquisition, to get actual numbers that are, especially on solar farms, oftentimes the system operates at a different value, voltage, for example, than it does on the nameplate. So always use real data if you can, as opposed to calculated data. The second point is also quite important. Arc flash studies don't generally concern themselves with equipment that doesn't impact incident energy. And why I say that is that, for example, we don't normally model things like solid blade disconnects and things like that in the system, because if it doesn't impact incident energy, they don't spend much time modeling that process. So you'll notice when you look at some of the models I'll show you, they're obviously absent things like disconnects, or in some cases circuit breakers that don't have an impact on incident energy calculations. Now, the next point is also very important, and that is, remember, when we talk about the term energy, we're always talking about an element of time. So in terms of incident energy, there are two things to concern ourselves with: the magnitude of short circuit current that's being released in the system, and the arc duration. How long does it take to actually clear the arc, the faulted element, from the system? So when we talk about incident energy, the magic number that appears in the regulations is 1.2 calories of heat per square centimeter of your skin. So it's heat per unit area. If you want to know what 1.2 calories of heat actually is, if you were to take a standard issue candle and light the candle, hold your finger 1 inch above the candle flame for 1 second, that is 1.2 calories per square centimeter of incident energy. And that will be the onset of a second-degree burn. So it's very important to understand that when we're talking about energy, we're talking about essentially how long your finger's in the candle, so to speak. And I'll use that expression more than once in the presentation because it's a good visual to think about. So when we're doing an arc flash study, we're not really changing the short circuit current in most cases. What we're doing is changing how fast the system will clear a fault. And so that is a function of fault current and the relaying and things like that that are in play. So for the rest of the presentation, remember, when we're talking about incident energy, we're talking about a magnitude of short circuit current and a duration, an arc duration in terms of time. The fourth point, or the third point, is also very important, and that is, as engineers, we do these arc flash studies for two different audiences. I always recommend that there's a narrative report that is understandable to anybody who doesn't have to be an engineer. A lot of what we do in these studies is giving management good information, hopefully, that they can use to make better decisions. Therefore, our job as engineers is to make these complicated concepts simple enough to understand for somebody who's not an engineer. And because, again, oftentimes we're trying to impact or influence a member of management who may not be technical. So because of that, we have to really get down to the basic level. And I call it the layperson check test, meaning that I encourage you to route the report to somebody who's not an engineer and see if they can understand what it is you're trying to say to them. What are we asking them to do as a result of this report? That can be very helpful. And I actually, in fact, do that. I give my report to a layperson first and see if I've used vernacular or something that is hard to understand for a non-technical person. And so because of that, that's, I think, a good check in the system. And then the last point is arc flash risk studies should mitigate or improve the arc flash situation, the magnitude of energy releases when we're able to do it. Technically speaking, the standards that relate to these normally don't require us to try and lower incident energy, although some do. So I say that because it is technically legal to just calculate incident energy on equipment that will be exposed or accessed in the field and just label it. So you could label it with a very high incident energy level that would be actually unsafe at any speed in real life. And of course, I recommend we take that a step further and try to actually lower the incident energy through the use of engineering controls. That's the focus of this whole presentation. So let's go to the next slide. Now, some of the unique hazards that you'll encounter on solar farms. Well, one thing that's not unique is that we have extremely high short circuit current on solar and wind farms. Remember, if you have a system that produces, say, 300 to 500 megawatts of generating capacity, if you have a transmission system that can receive 500 megawatts of generation, If there's a fault on the farm itself, of course, it'll give you that back and some change as well. So we always need to realize when you're working with systems that can receive that kind of generation, there's a tremendous capacity there for short circuit current as well. And that has to do with something called equipment duty. Equipment duty is a concept that it actually compares the actual interrupting rating of a protective device to the actual short circuit current to which it would be subjected. So equipment duty is very important because if you have a circuit breaker, for example, that is not able to interrupt the fault current that's present on the farm, you'll have what's called a through fault. And that means that the current will go through that overcurrent device like a bullet, like it's not even there, and it will not be able to interrupt the current flow. What usually happens then is the next upstream device will clear the fault, or the worst of all scenarios would be that you actually burn in the clear. You melt the conductors or the bus bars, and it eventually clears itself. Of course, when you have those kinds of events happening, your finger's in the candle a long time, so to speak, and incident energy would be deadly. It would be unsafe at any speed. We have done arc flash studies and found that even the 34,500 volt circuit breakers in a substation were actually over duty. There was more short circuit current there than they could interrupt if it was an actual fault of that magnitude. So equipment duty is a very important concept to consider. And even in substations, we've had experiences where you could have, as I said, overcurrent devices that were not able to interrupt the current flow. And that, of course, is something that we need to address from the engineering side when we're able. Another point that's not directly related to arc flash is that we have unusually high low voltage systems on both wind and solar farms. Before green energy really came into play, we had typically a low voltage system was considered a class 600 volt system. The utilities only warrant that they'll give you voltage within 10% of the nameplate voltage. So give or take 10% of a 480 volt system would be up to 528 volts. And historically, the codes called high voltage systems 601 volts and above. So anything below that was considered low voltage. Well, of course, now the wind and solar farms have come into play. Our low voltage system, so to speak, or the low voltage side of a transformer, for example, may be much higher than 600 volts. Solar farms, the wind farms now are running at 1500 volts. And they're still low voltage systems. They're configured in the manner of a low voltage piece of equipment. So therefore, things like lockout, tagout, and all that on low voltage systems that are still more than 600 volts, we're still going to use low voltage techniques to do that. So why this is important, for example, is you may have a piece of equipment that runs at, say, 860 volts, and it will be, even though it's more than 600 volts, you're going to follow low voltage procedures. In other words, you wouldn't, for example, put on personal protective grounds. You wouldn't be required to do protective grounding on low voltage systems that are configured like that. So it's kind of an important point, and I imagine someday we'll change the codes to agree with that. But at the moment, low voltage systems is really how it's configured rather than the voltage it's actually operating at in the system. The third point, very important for solar farms, and it's called thermal cycling, sometimes known as thermocycling of circuit breakers. And what we mean by that is, of course, with a solar farm, you get a scheduled outage every night. So the system will run at maybe 107% of nameplate during the day and something considerably less at night. So this heating and cooling of the circuit breakers really puts a premium on your maintenance of the breakers as well, because the temperature, of course, is the enemy of our insulation in the system. So when you run a system at high temperature, it breaks down more quickly. For example, in the utility industry, we usually fuse transformers at, say, 150% of full load on the transformer. If you do that, the heat that develops in a transformer at full load will actually, where the transformer will essentially fail at about 22 years of operation. Double that to a 300% of full load, and the same transformer will essentially fail in about 7 years. So the heat is the problem. And of course, solar farms are usually in a desert, someplace where you have a lot of sunshine, and just the ambient temperature might be 120 degrees, and then operate the system at full load plus a little bit more. And you can imagine that it's extremely hot in there, and then it cools down at night. So this thermal cycling really puts a premium on maintenance, breaker maintenance in particular, in the low voltage transformers and low voltage side of transformers. We'll talk about that as we go. There's also a fair amount of unusual equipment, and this falls under the training category, qualified electrical worker requirements. for solar farms. And I mention this because the technicians on a solar farm have to have a lot of additional training. Say, for example, if they became a journeyman electrician in the industrial world, moving over to a solar farm would require very specific training that they wouldn't normally get. So, for example, solar panels themselves are a unique piece of equipment in the sense that they shut them off, so to speak. So that's an important piece of training that they need to receive. 3-winding transformers, transformers that share a primary winding. So you have a high voltage winding and 2 low voltage windings that feed discrete parts of the farm. That's a piece of equipment for which employees or electrical workers would require additional training. Inverter skids are also a piece of equipment on a solar farm that requires special training. Workers may be fluent, for example, with inverters and pad mount transformers, but here we have them put together on the same skid. So we have an alternating current side and a direct current side of an inverter system, and each having unique hazards. Some of them we will cover in this presentation. Of course, the combiner boxes, where all those solar arrays come together in a combiner box, where of course they're combined and then conducting to the inverter skids. This is how the generation process happens. So combiner boxes have their own discrete hazards, shock and arc flash hazards, and we will cover those in the rest of the presentation. Something that's not unique to solar, but wind and solar, is very common to have bottom-fed equipment, meaning you have a circuit breaker mounted in the system, and it's actually the source side is actually the bottom side or the low side, the part of the system we normally expect to be switched off when you open the breaker. Well, it's very important on wind and solar farms that we always assume either side of an overcurrent device can be energized, realizing that very, very often system is bottom fed, which is a non-standard way of looking at how these systems are mounted. Nothing illegal about it. It's just that workers have been electrocuted when they open up a system and even do a voltage check on the wrong side of the equipment and realize that it's energized. And then finally, sulfur hexafluoride switchgear, SF6 switchgear. There's a kind of a unique kind of a switch that often exists on these solar farms, and it is exactly the same switch that you'll see on wind turbines when the turbine itself, when the transformer is actually up tower. So you'll find these sulfur hexafluoride switchgear that they work on. They require special training to make sure they're functional to use, and they also have lockout tagout implications that I really won't go into here. But locking out and tagging out SF6 switchgear is a unique skill that you'd want to include in your training for qualified electrical workers. So we'll go to the next slide. Now, the direct current equipment, I've kind of covered this, so I won't spend too much time on it. Of course, we said you can't shut them off, at least completely. So because of that, there's often a shock hazard there, even when there isn't a lot of irradiation outside. Now, the next point is important. Photovoltaic direct current equipment usually, but not always, don't present a significant arc blast hazard. You should be aware that in the electrical regulations that relate to anything other than solar and wind farms, when we actually talk about arc flash hazards for clothing, it really wasn't the initial arc blast that was the problem. What was the problem is there would be a blast of such magnitude that it would knock the worker either unconscious or knock so silly that they can't participate in their own rescue, and their clothing would start on fire. So they'd essentially be knocked out and they would die being burned to death by their own clothing. So early on in the arc flash protection world, this would be about the year 2000, we started realizing that we have to do something about that. So we were in those flame resistant clothing back then, now known as arc rated clothing now. And in fact, we're realizing that you could still get knocked out, but at least you wouldn't die by your own clothing being on fire. And of course, since then, we've taken it a step further. We've not only prevented you from dying from your own clothing, but we've actually insulated you from the electric arc. And that's kind of where we are today. Having said all that, the DC side of a solar farm does not have a lot of short circuit current. The short circuit current on the DC side is about 1.1 full load amps. So unlike the AC systems where you can have an arc blast that could knock you out, you actually can self-rescue usually from a DC fault out on the arrays, because the arc energy is much less. The arc flash boundary is often very confined, maybe 18 inches or just a few feet. So because of that, DC systems normally, but not always, don't present an arc flash hazard of any significant magnitude from the explosive side, from the blast part of the discussion. And then high IE levels or incident energy levels on systems relate mostly to the fault duration and not the magnitude. And I'll show you some pictures of that in the next slide or so. Okay. Here we see a system where we've had a raceway on the DC system coming in that completely melted into a puddle of molten aluminum. What happened here is it was a relatively low capacity fault. However, it continued to burn for so long that it melted all the enclosure. And by the way, this fault got started by mice, actually. The mice chewed through the wires and initiated an arcing fault. And you can see it lasted long enough to actually melt the entire raceway. So if you actually calculated incident energy, it would calculate the several hundred calories of exposure. So while you would think that would be unsafe at any speed to work around that, in real life, the arc blast part of it is not very significant. And so this is absolutely high calculated incident energy, but the difference is, from a safety perspective, its blast potential is quite low. And if you did have an arc flash in those situations on that part of the system, it usually doesn't result in a very significant arc flash hazard because you are able to self-rescue. Let's go to the next slide. Now, inverter skids, interesting piece of equipment that requires some thought on both the arc flash and the training aspects. So first of all, the AC side of the inverter does absolutely present significant arc flash hazards. The AC side of that can have hundreds of calories of exposure and very significant short circuit current, very high fault current. So the AC side of the inverter does act like every other piece of AC system equipment that you've modeled in the past. It just is essentially a pad mount transformer and some conductors going into some switches, and we'll talk about that in a moment. Because you have this extremely high short circuit current, we talked earlier again about equipment duty. Well, that's absolutely in play on the AC side of the inverters, and any breakers or switches that are used on that side of the equipment. And then you also encounter something on this that's maybe unique, and that is the DC switches may not be relay controlled. In other words, they may be actually used just for a switch. So, for example, I've got a picture of this IntelliGuard. You see it's a low voltage DC switch. Well, in this case, there is no, I should have had the slide pictured, on the upper left side of that same name faceplate, there's a place where you could put a trip system and a trip relay in there. But in this case, this is absolutely used just as a switch. And in an incident energy calculation, it would have no value at all. It's essentially a bus bar as far as we're concerned from the arc flash standpoint. So on this, you do encounter this on solar farms where you may have a three-phase breaker used as with individual phases, or you could have three single-phase breakers used on this side of the system. So it's a rather unique piece of equipment from a training aspect. And from an arc flash standpoint, we ignore any DC switches or AC switches that aren't controlled by relays. They have no impact on incident energy at all. And then the picture on the lower left side is on the DC side of the system. These are going to be where the combiner boxes come in. When they comes in from the combiner boxes into the inverter. And we'll talk a little more about that. But remember that picture in the lower left side, that's going to come up more than once. Now, another rather unique piece of equipment that you rarely see except on solar farms is a three-winding transformer. Now, again, with transformers on solar or wind farms, we don't use primary versus secondary vernacular. We're going to use the high voltage side versus the low voltage side because the source varies. when a system like a wind farm is not generating, the source could actually be the substation feeding it. That can change when the generators are actually generating at full output. But just I got this picture because it's a really good picture for a solar farm because it illustrates several different pieces of equipment that you often don't see except on solar farms. So in this case, we've got the left side of the high voltage compartment there where we have our 34,500 volt switches or feeders or conductors. Now, again, when you look at the transformer, the H1A and H1B are the same conductor. There's a bus bar that goes between it, and it feeds through. In this case, this would be the last transformer in a string of transformers or a circuit of transformers. And you'll notice the very last thing we have on there is elbow-mounted lightning arresters. Now, lightning arresters have a history of failing. Phase-to-ground faults often happen with lightning arresters on them, involved in them, and in fact, they can come out with some force. We've actually had lightning arresters get shot right through the door, actually, with the amount of energy that's released in some of the faults on these systems. So here we see a system where we have the 34,500 volt system on one side on the left. On the right side of the same system, we have lightning arresters installed. If you look in the top part of the slide, you'll see there are three what we call well-type fuses. Those are expulsion-type fuses, and we're going to talk about the differences between expulsion fuses and current-limiting fuses in just a moment. But what's interesting about this is you can actually change those fuses. So from the engineering standpoint, this does give us the opportunity to refuse current characteristic curves. So we can actually sometimes lower incident energy even on the output of the system by changing the fuses in the transformer. Normally, the expulsion fuses in a pad mount transformer are under oil in the tank. They're actually sitting on the bottom of the tank of the transformer, and you can't do anything about them as far as changing them. Solar farms especially often have these well-type fuses, which gives us choices from the engineering side. On the right side of the slide is the low voltage compartment on the same transformer. Here we have two circuit breakers in there that are internally mounted in the system. In this particular case, they operate at only 270 volts. So the other side of the equation, right? We talked earlier that solar farms can often have systems that run at 900 and some volts or more. 860 volts is a common voltage. Yet in this case, we have parallel systems, two 270 volt circuits that come out of there, and then the circuit breakers at the source of that, well, the circuit breakers in that system are right in the pad mount transformer itself. And we're going to talk about that from an incident energy calculation standpoint here in just a second. We'll go on to the next slide. Now, this is an important concept for us to consider as engineers as well, and also as workers. What you have on the secondary side of the transformer, the low voltage side of the transformer, you have that same thing coming up. In this case, it's bottom fed into that particular breaker that you see there. So many times workers would say, well, I would never take voltage readings, for example, right in a pad mount transformer because of the explosive potential here in the transformer, yet they would go into the inverter skid itself and take voltage readings on that breaker there. So we'll talk about that, but realizing where you take your voltage readings matters from both a shock hazard, but also from an arc flash standpoint that we want to talk about. But do keep in mind that whatever you've got on the secondary side of that transformer, that low voltage side, wherever that comes up in the switchgear, absolutely can represent an arc flash hazard, and it can be very significant. Now, let's just take a look at the incident energy at various points in the system here, and also at different current levels. You'll notice that in this case, the top of that breaker fed directly from the transformer. And this is important to understand that the overcurrent protection in a pad mount transformer is on the high voltage windings, not on the low voltage windings normally. So normally when you have fusing on a transformer, it only is protecting the high side of the transformer, and we'll talk about the significance of that from an arc flash standpoint right here. So here we see a few different scenarios. If we're on the side of that circuit breaker that's connected directly to the low voltage winding in the transformer, the overcurrent protection is only seeing a fraction of the fault current that you're seeing on the low voltage side, and we'll show you that in just a minute. If we calculated that out at 100% of the arcing current, it would calculate to 515 calories of incident energy on the secondary side or the low voltage side of that transformer. If we calculated that at the 85% level, it would increase up to 890 calories. And of course, when you're talking about 890 calories, it probably wouldn't last 12 seconds, as you can see. It would probably melt in the clear before that time. But from a calculation standpoint, it would be considerably higher. Now, if you use the recommendations in the 1584 regulations, they would suggest that we clear all faults in 2 seconds or less. If that were true, it would calculate the only 114 calories of incident energy. Well, of course, it's very significant. But if we actually if we use the secondary breaker and it cleared, you'll see that it clears in only 3.8 calories. So looking at that little graphic there, if you took your volt readings on the high side or the source side, if you will, of that circuit breaker, there'd be 500 calories. On the very low side of that same exact breaker, there would only be 4 calories basically in the system. So this is important to consider from a safety standpoint for training, but it's also important from the engineering standpoint. If we can do anything to lower that incident energy, we can get it from where it would be certain death at 500 calories down to 4 calories, which would be survivable wearing street clothes, essentially. Let's go to the next slide. Now, from an engineering standpoint, the transformer nameplate is very helpful. Here we see that this particular transformer is 12,470 volts on the high voltage winding, but only 270 volts on the low voltage windings. Now, if you take a look at it, you can see that they have the symbology there that shows you on the high side winding or the primary winding. I'm sorry, I broke down. My high voltage winding is wound delta, and if you took the time to look at the low voltage windings, they are wound Y. Now, you'll notice that they actually have the fusing illustrated in the actual graphic, the schematic that you see on the nameplate. For example, you see the feed-through bushings we talked about earlier, H1A and H1B feed-through. Then there's a disconnect on there, which is the rotating switch that you operate with a shotgun stick. And then the important part I wanted you to see. You will see that there are 2 fuses in series with each other on the high voltage winding. One is called an expulsion fuse, and one is called a high current limiting fuse. Why I'm telling you this is that the expulsion fuses on a pad mount transformer only have an interrupting capability of about 1200 amps. So if you only had expulsion fuses and those well fuses that you had earlier that I showed you, a fault on the primary winding, the high voltage winding, would be a through fault. It would not be able to interrupt the current flow, and the fault would go all the way back to the substation. You'd actually have to clear the entire 34.5 circuit in order to clear that. The fix for that is to put a second fuse in series there, which is a current limiting fuse. So why this is important is if you had a high voltage fault on the primary winding, the current limiting fuse would clear that expeditiously. It was normally very good at clearing those high fault current events. And the expulsion fuse would clear low voltage winding faults on the system. So this is also important to keep in mind. So again, having the 2 fuses in series with each other is critically important. And as engineers, we want to spec out which fuses, if you have a choice to order the transformers, to be able to pick the kind of fusing you're using can directly or greatly impact incident energy from the engineering side of the house. The other thing we're going to talk about is the transformer turns ratio. We're going to get that in just a moment. But you'll actually see that on the left side of the transformer, there's a table A, B, C, D, and E. Those are the tap settings on the transformer itself. The C winding is always the nameplate rating of the transformer. So you'll see at 12,470 volts, they've calculated full load current at 46 amperes of current there. Just file that in your brain because this is going to be a useful calculation we'll show you here in just a second. So in this case, if you did the transformer turns ratio calculation, you just simply take the high voltage divided by the low voltage, and that will give you the ratio of current flow on each winding. So in this case, 12,470 divided by 270 is 46 amperes. So this means that for every 1 amp you have on the 34.5 side of that, the 12 kV side of the transformer, you would have 46 amps on the low voltage winding. And this is very important from an arc flash calculation. So why do we care? Well, let's take a look. What we're trying to do here is that this curve you see is a rough estimation of what a time current curve for a fuse would look like. It's an inverse time fuse, as you can imagine. So here we see if we have very high fault current in the system, the fault clears on the x-axis here is the time, the clearing time. The y-axis is the fault current level, the short circuit current. So you see if we have very high fault current, the clearing time is relatively brief. Take the same curve and have much lower short circuit current, meaning a higher impedance fault in the system. This translates to much higher incident energy levels. Let's go to the next slide. Well, actually, we're all the way to wind farms right now. So we're gonna talk a little bit more about the time current curve issue in just a moment. Now, on wind farms, there's similarities in the sense they also have very high short circuit current values, and equipment duty is very much in play for them as well. That's a very important concept for them to keep in mind. Again, they also have very high low voltages in the system. So when we talk about that, I'm understanding now that we have wind generators that are generating at 1500 volts, yet the low voltage windings are just that. They're configured as a low voltage winding, even though they are actually operating at considerably higher voltage than we used to consider low voltage. There's also unusual equipment on solar farms that require training. For example, the doubly fed induction generators. Well, again, calculating short circuit current on those is useful, but better still to get the manufacturer's information from an engineering standpoint. They will tell you what the generator will output in a fault. Definitely use that data if you can, rather than using calculated values, because they have a better insight into that than we would just calculating it. There are also power factor correction capacitors, which have a bad history of exploding from time to time, more of a safety training aspect, but there's a unique piece of equipment for which they need particular training. And then in some cases, and what you see in the picture on the right is an example of this, some turbines are configured where they actually have 34,500 volt transformers up tower. I don't like that very much, but actually it's actually a unique situation you'd find on a wind farm. I'm sorry, on a wind farm where you actually have high voltage windings, 34,500 volt windings up tower in the nacelle itself. And that requires specific training on grounding and lockout tagout. And finally, the type of switchgear you'll find on a wind farm is often sulfur hexafluoride switchgear. Identical switchgear that you see on a solar farm, and it's used in this case on a wind farm generator, wind turbine generator. So again, it requires special training for both lockout, tagout, and grounding. Let's go to the next slide. Now, modeling solar and wind farms. So I'm going to give you some insight here, and some of this, as I said, I've taken from other engineers that operated very clearly. Now, from a macro view, what we've got going here, the bus that you see to the right on the macro view is actually the inverter. That's the incoming DC side of the inverter itself. What you see there in this case are all the combiner boxes where we've aggregated all the arrays into the combiner box. And each one of those combiner boxes represents the actual current that would be produced by the solar array in each of the combiner boxes. Now, this is one place where I strongly encourage you to actually use the information you get from SCADA rather than just calculating the output of the farm. There's many cases, for example, where the voltage of the system is supposed to operate at 860 volts DC, and in fact, it operates at 916 volts all the time. So use whatever the actual data is on SCADA rather than just calculating the values, because it sometimes can be quite different. So in this case, what the engineer has done is they've aggregated all the feeders into the combiner boxes, and I think there's 12 combiner boxes that come into that particular inverter. So from a macro level, it just gives you a view of how they chose to model that part of the system, the DC inputs into the inverter itself. Down below it, you'll see more of a micro view where you're actually seeing what they've done. So the photovoltaic symbol you see in the box, and those 400 amp fuses that you see in the circuit were the ones I mentioned to you earlier, those white fuses that were coming in from the actual photovoltaic arrays into the inverter itself. Now, if we take a little bit closer view at that, what you're actually seeing from the source side of this, the thing breaker label way number 1 is actually a 34,500 volt system. It is an SF6 breaker, and it is relay controlled. It is in a pad mounted switchgear. You'll notice the transformers themselves have those 2 fuses, as I mentioned. You'll see the high-tech OSS fuse is a current limiting fuse, and the ABB protective link is an expulsion fuse. And we've already talked about the significance of that. And then it comes into the pad mount transformer actually in the skid itself. And in this case, you can see it's a 1360 kVA transformer, 1.36 MVA transformer. And if we take that a little bit further, we can actually show it down to the transformer level on the solar farm, where we have those 2 fuses. It comes into the primary winding or this high voltage winding. And then what's on the secondary side is actually the input from the inverter itself. So if you look at the macro view and the micro view, you can sort of see what's happening on the solar farm side. Now, if we take the same model for a wind farm, and I want to make sure I get done here in a timely way, The substation itself, and this would be true of the solar farms as well, the substation itself, we normally model using differential clearing on both the main transformer, the GSU or generator step-up transformer, and also the 34.5 bus is most often protected by differential relays. We'll talk about how to model that in a second. But in a substation, we generally don't use time over current calculations as much as differential clearing, because in most cases on the sub, transformer, and bus, they usually are cleared by differential relays, and that will absolutely be the fastest clearing you're going to get in that situation. Now, if I take this a little bit further, and so you can actually see the turbine generator itself, starting from the bottom and working our way up, the bus that you see labeled there as, I think it's 1-01, that is actually the feed-through bushings in the transformer. That's H1A and H1B. The engineer in this case chose to model only the expulsion fuse, because on faults on the generator side of that transformer will not be cleared by the actual expulsion fuse itself. So it's up to you as to whether you want to put both fuses in series with each other or not, but on faults on the low side, only the expulsion fuse will clear it. The engineer in this case chose to do that. You'll see that the ABB Sachi breaker is usually our main circuit breaker on the wind turbine side. That's often labeled CB1 or Q1 in some vernacular. And then we have the low voltage windings all the way to the generator itself, where we have another breaker in the nacelle and then the generator itself. And once again, getting the fault current from the generator from the manufacturer is normally what we recommend. But otherwise, you can just simply do a short circuit calculation to get your bolted fault current. And then using the formulas in the 1584, you can produce arcing current and use that if needed. But again, normally we model that just as an induction generator, and that gives us a pretty good rendition of short circuit current on that part of the farm. So to avoid some basic traps, well, one thing I recommend is don't hyper-focus on the high voltage equipment. Although realizing from a work practice standpoint, any work done on high voltage windings, and in this case, we're talking about, your 12 kV and above, normally that's all done with insulated sticks. You're rarely ever doing that right in the gear itself. So from an arc flash standpoint, your low voltage systems often are more dangerous than the high voltage, simply because normal work practices would have you some distance away on high voltage systems. Don't blindly accept the results of power system software. Each software has its own advantages, whether it be Easy Power or ETAP or whatever you're using. We'll talk about that a little bit later on, but it's important to get to know your software and know what it does well and what needs some interpolation or whatever the case may be, and use that knowledge to temper the results you get. I often use a database. Each software usually has a database browser in it, which actually has the settings on every breaker and every footage on cables, whatever. I definitely use the database browser to make sure that the settings you have on your devices are correct, and that every unit in the system is in fact going to operate. In other words, it's connected to the system and it won't actually interrupt current flow. Many times, if you forget to enter the data of a piece of equipment, it may allow you to run the calculations, but it obviously wouldn't take into account the clearing time or the response time of the system if you didn't have that model properly. So use the database browser to make sure that all the system has appropriate inputs into them and they will operate using proper calculation methods. So some modeling tips, again, that will sum this up and we'll bring it to closure. As I said, most buses and substations are protected by differential clearing. This would be your 87 relays. So when you see an 87 relay, it's a differential relay. Contrast that with an 86 relay, which is a lockout relay. So the 87 relays usually drive the 86 relays, in which case it will operate multiple breakers at the same time. So in a substation, for example, you may have to clear multiple circuits simultaneously, and that's what the 86 relays do. It's essentially clearing each individual device. It gets the trip signal from the differential relay, the 87 relays. I already mentioned this earlier. Get your short circuit calculations from the manufacturer when you can, and get actual operating voltage and current from SCADA when you have the opportunity. Once again, combiner boxes, for example, the actual amount you have in there may be considerably different than if you just did a straight calculation. So take that into consideration as well. And then consider putting nodes, calculation nodes, on both the source and the load side of your overcurrent devices. That way, the system will calculate incident energy on each side, and it will become apparent to the workers in particular where the hazards are in the system, and it'll help them make better choices out on the farm. So, power system software you use. Understanding how the software thinks is important because, again, each one has its own little biases, it seems. And so make sure that the values you get, it doesn't even hurt to do a few hand calculations to verify that the software is giving you an expected result. And that is true of pretty much any software, I think. They also may have workarounds for the limitations. So I spend a lot of time talking to the company who produces our software when we come into a situation where, because of the age of the equipment or the way it's configured, the software is having a hard time giving us an accurate calculation. They often will give us a workaround for that, and that's a very helpful thing from the engineering side. Apprentice yourself, work with an engineer who has experience doing the studies and also experience with the software you're using. I think that would be a good exercise for all of us to do. And of course, take time to get good data. Go and gather the data. Do whatever you got to do to get good information. And of course, make sure that you have accurate numbers before you actually start doing the calculations themselves. So that's the end of the presentation. As I said, I hope this was helpful to you. I am not actually seeing any of the questions just yet, but I'll wait for Banu. Maybe they're getting questions, and I'll try and answer your questions before I go. If you don't have questions, thank you for taking the time to listen, and I hope this was helpful to you.
Hey, John, can you hear me? We have a few questions again, so...
Banu, I'm getting all kinds of feedback, duplicate sounds, so if you can shut one of those off, so I can't understand you.
Give me 1 second.
That sounded better, whatever you did.
Can you hear me now, John?
Yeah, that's much better. Thank you.
So the first one is, what are the PPE category levels as per incident energy levels for DC systems, or the same as AC?
Yeah, the calculated incident energy will be you're going to use the same values. It's just going to calculate differently. So the software now will give you calculations on DC systems. You may have to interpolate a little bit about that, but whatever the calorie number calculates out DC or AC, you're going to use the same kind of protective equipment.
Thanks, John. The next one is, don't you need to have the switches and circuit breakers in the model to verify the fault duty of the equipment is sufficient? Also, don't they need to be labeled as their equipment that may be interacted with?
Yes, you definitely want to put circuit breakers in the system where they exist if they're going to be over duty. Remember, a fuse, we're talking about fault current exposures here. So if you have a switch, the reason we don't worry about that is it's going to stay in the closed position throughout the fault. It's just a solid piece of cable. The reason we're interested in equipment duty is we're expecting that device to interrupt fault current. It's going to act and do something. So we're not just modeling it because it's in the system. It's not going to be over duty if it's just continuous current normally. Although I suppose it's possible if they've engineered a bus bar such that there's more fault current there than the device can handle just for conducting current, well, then you'd melt the device. But normally speaking, the reason we don't worry about switches is that they're not interrupting current flow. They're just conducting it. And when you'd operate the switch, it would normally be for routine switching. You wouldn't be doing the switching under fault duty. I hope that helped the person who asked the question.
Thanks, John. The next one is, do you see a lot of aluminum conductors on solar farms, and do you see issues with thermal cycling?
Yes, I do see. I've often seen aluminum conductors on solar farms and even on some wind farms as well. And the second part of your question, I didn't hear.
So do you see any issues with the thermal cycling?
Do I see any shields?
No, issues. Any problems with thermal cycling when you use aluminum conductors?
I haven't actually seen it myself where there's a difference between them. The thermal cycling normally affected the breaker itself, in my experience. That doesn't mean that it's not an issue, but certainly normally we've had the issues I've had with thermal cycling was on the breakers themselves. Although we have had a couple of scenarios where a conductor actually burned in the clear mid-span between two connection points. It's very rare for that to happen, but we have had that happen, especially when when cable training is particular. You make a sharp bend in the cable, and often that point will concentrate heat and melt the conductor. And in that case, aluminum would be more susceptible to that than copper. The answer to the question is yes. I've seen them on both wind and solar farms. I can't say that I've seen the conductor being the problem very often. It's mostly the breaker itself.
Thanks, John. So the next one is, how did you come up with 1.1 times for full fault current in PV systems?
Just take a look at the actual nameplate of the array itself, or the panel itself, and it'll give you the normal current rating and then the fault current on the same panel, and you'll notice it calculates to about 1.1 what the normal current output is, and that can be extrapolated to the whole farm. Everything will be about 1.1 of what full load is.
Thanks, John. The next one is, for inverters, do we provide arc flash label as per DC or AC?
I would put both. So now that we're able to calculate it on both sides, you'd want to have a label for each side because they're very different.
So why is it better to use fuses instead of circuit breakers?
Well, it's not always better to use. It's just that in terms of current limiting fuses, the advantage of a fuse is that it will interrupt current flow where a circuit breaker may not be able to handle that. That being said, the problem with fuses is that you can single phase the device. You can have one phase trip out and it won't necessarily gang operate. So from a fault standpoint, ideally, we'd like to have all three phases. If it's on the AC side, we'd like to see all three phases clear at the same time. So each thing has its advantage. You have to use the device for what it's good for. So if you got a high, tremendous short circuit current, a current limiting fuse is worth it to use it because it prevents the device from exploding, for example, but you have the problem of single phasing. Circuit breakers have the limitation that they can only interrupt a given amount of current flow, say 65,000 amps, which is normally plenty good on a wind or solar farm. But again, each device has its advantages. So from an engineering standpoint, we use whatever device gives us the best protection and manage the limitations however we need to do that.
Okay. So the next one I have is, why arc flash study is considered differently from relay coordination study?
Why is it different?
Yep. Why is it different than relay coordination study?
Well, a relay coordination study is part of an arc flash study. Normally, I mean, we have to take that into consideration. But what is a bit different about them is the relay coordination, we're mostly interested in the system tripping out in the right order. And an arc flash study, we're interested in lowering the incident energy. So why that's important is in some cases, you may have two overcurrent devices in series with each other. And from an arc flash standpoint, we don't care which one trips out because the net result is the same. You're going to lose the function of the device. From a coordination standpoint, we'd be unhappy with that because we took out a larger part of the system than we'd really want to take it out. So again, the relay coordination study is saying where everything is tripping out in the right sequence. The arc flash part of that is we're interested in lowering the incident energy. So from an arc flash standpoint, I'd be happier with a miscoordinated system that trips out and gives you lower incident energy as long as the net result in the system is the same. So that's the difference. The relay coordination study is proper sequencing. The arc flash study is mostly interested in lowering incident energy. That being said, a home run would be if you get both. If you can have it sequenced properly and give you low incident energy, well, of course, that's a home run if we can do that.
Thanks, John. The next one I have is, what does it mean short circuit current for generators?
It means that when the generator is feeding a circuit that has a fault on it, what is the maximum amount of current that generator will supply to the fault?
Give me one more second. So one question I have is, which is the good resource for further study in the arc flash?
Well, you can certainly read the 1584 standard. That's very helpful. That walks you through it's kind of a walk through history of how we calculate the various nodes, and it has every calculation that we use in the system. So I would say begin by reading the 1584 standard, And then other resources, I mean, other than taking, as I said, and I've done this myself, I've taken advanced training with the types of software that I use. And of course, having proper training in relaying and system protection is also so important. And it kind of depends on what kind of electrical engineer you are. If you came up more with controls or computers, you'd need to have considerable additional training in system protection. On the other hand, if you came up on the power side of the system, you're probably already versed with most of the things you need to know for an arc flash study. I guess augment whatever gaps of knowledge you have, and I would certainly include in that advanced training in the software, as I mentioned.
So with differential protection, what time delay needs to be added for switching transients when breakers are located between the CTs?
Okay, say that again. I need to hear that one more time.
So with differential protection, what time delay needs to be added for switching transients when breakers are located between the CTs?
Normally, from an arc flash standpoint, I don't add time to that process, because if there's the differential relay is, of course, comparing incoming and outgoing current. If there's a differential there, I want it to trip out. I would rather have a miscoordinated trip on differentials, because differentials are usually protecting the most expensive part of the system. So if I'm protecting a power transformer, for example, I don't normally try to add timing in that, because if there is a fault of any kind, I'd rather have it trip out incorrectly than to damage the equipment catastrophically, if that makes sense. So that being said, well, that's my best answer. May not be a good one, but that's my best answer.
Okay, thanks. So the next one is, I understand that a disconnect may not add to the fault current. However, as an engineer, you should ensure the labels are generated to help those individuals who are performing the switching. Do you have any comments on this?
You say it to me one more time. I'm trying to process the question.
So the question is, the disconnect may not add to the fault current, but you need to use the labels are generated to help those individuals who perform the switching. So how do you justify? Do you want to add any comments to that?
Well, the switches don't add to fault current; they just conduct fault current, and so they're just one series element in the circuit. It's like I said, you can visualize it as if you just took the switch out and just pasted in a solid blade bus bar. So they don't labeling them is whatever the equipment is that they're actually working on is where I want the label, not the switches that feed the particular equipment. So when the worker is accessing the equipment protected by an upstream breaker, I'm interested in both the source and the load side of that breaker itself. And remember, the source side of the breaker will be the same as the load side of whatever is feeding it. So the labeling will be any place that would be accessed by somebody doing maintenance in the field would require an arc flash label. That's what the 7D requires. So the switch itself is just a series element in the system. If you want to put nodes on either side of it, you certainly can. But from an arc flash standpoint, it's just going to sit there in the closed position while the fault happens until some.
So what options are there when the calculated arc flash value exceeds the protection of the highest PPE available in the market?
Then you're going to do what the 7E calls a special precautionary technique. And what that will be is it can be anything from, most often the solution is closing it in remotely, either using SCADA, that's plan A. Plan B would be to use, an unfortunate term, a chicken switch, which is it's a temporary device you can magnetically connect to the handle on a switch and actuate a breaker remotely, or using an insulated switch stick to add distance between you and the arcing energy. Any of those are possible solutions when you have more incident energy than you can handle. But the most common thing you're going to do is put additional distance between you and it. And finally, another very useful thing is on some relays, like on your high voltage relays in particular, you can use something called maintenance mode, which allows you to temporarily change the pickups on a relay once the system is actually operating. Now, I didn't go into this because of the timing, but when you're actually talking about, well, hang on. I lost my position. I lost my place. I'm sorry. Repeat that one more time. I had a brain fart there. Banu?
Arc flash PP in the market is what they asked, John, right?
Oh, okay. You just broke up. One more time.
So the arc flash PP availability and the calculated arc flash level, if they exceed what they need to do, that's what you answered.
Yeah, I'm sorry. Yeah, if you have more incident energy than the clothing can protect you from it, then you'd want to exceed minimums there by doing something. And maintenance mode is what I was talking about. It allows you to not have to set the relay to be able to start up those transformers, the inrush current on transformers. So if you had a circuit coming out of a substation on a wind farm, for example, and you're going to turn on that circuit, every transformer in series in that circuit would have a tremendous amount of inrush current. And if you don't have the relays set to allow that current to flow, you'd have a nuisance trip. It would trip out. The opposite of that is what I'm suggesting here. If you use maintenance mode, you assume the system is already running, and you can set the relays much lower to give better protection. And the only danger there is if you forget to reset this when you're done, you'll get a nuisance trip on the system. But maintenance mode is another very effective engineering intervention we can use to protect people.
Thanks, John. I think we'll take the last one more question. So this is when the arc flash incident energy on the one side of the breaker is high and the load side it is low, do you not have to assume the worst case scenario for the label of that cabinet?
A great question, and the answer is it's up to you as an engineer. The two schools of thought, there's an option in the software usually called ignoring main, which means you set the software to assume that whatever fault you have is going to produce enough ozone to migrate into the other side of the breaker. That approach is effective in the sense that you'll never underprotect anybody. They will never be surprised by the amount of incident energy that's there. The trouble with it is that if you actually had that system, you almost always will be calculating extremely high levels of incident energy, and you will really never get the benefit of you'll be hamstrung for the work you're doing, because everything will calculate to very high incident energy levels, and that's the downside of it. That's not a right or wrong answer. It's your call as an engineer.
All right, thank you, John. I think that pretty much concludes, and then. The general statement for all the attendees, everyone who attended the webinar will receive the certificate of completion and a CEU, a certificate. That's the one thing. Second thing is the recorded version will be made available on YouTube, Facebook, and also LinkedIn live channels. You can go and watch it again if you want to just share it with your colleagues at your workplace. Third thing is Nick will be sending out copy of the PowerPoint presentation for all the attendees of this webinar. Okay. So with that, again, thank you so much, John, for doing this for us. Okay.
Thank you all.
Have a great day. Bye-bye.